Okay, so we have seen how um, the notion of a Fourier series for a periodic function can be generalized to the notion of a Fourier transform for a non-periodic function, and how the summation of the series expansion now becomes basically an integral, right? So it's called Fourier integral, and a function can be written as a Fourier integral, right, in terms of the inverse Fourier transform, and then there is a forward Fourier transform which gives you the Fourier transform of the function, right? So very often in practical applications, it's we encounter functions which may be non-periodic, right? So for transforms are pertain to functions which are non-periodic, but they are either even or odd, so they have well-defined parity, and in such a scenario it's more convenient to work not with the full Fourier transform itself, but define a special kind of Fourier transform, which is either a sine Fourier transform or a cosine Fourier transform. So this is going to be the content of this lecture. Okay, so we have seen how any arbitrary function f of x can be written as an integral minus infinity to plus infinity g of alpha e to the I alpha x d alpha, and then where g of alpha is the Fourier transform of the function, which is given by another integral 1 over 2 pi integral minus infinity to plus infinity f of x times e to the minus I alpha x dx, right? So it's important to mention that this factor of 1 over 2 pi which appears in the definition of g of alpha is a matter of convention, right? So the rule is that if you put a coefficient c1 in the first equation and a coefficient c2 in the second equation, the product of these two coefficients must be 1 over 2 pi. So you will see in different textbooks different ways of dividing these two factors c1 and c2, right? So very common convention is to use 1 over square root of 2 pi in each of these integrals, right? So sometimes you may find 1 over 2 pi in the other in the definition of f of x and so on, right? So it doesn't matter, right? So there's nothing sacrosanct about what definition you use. So the important thing is, of course, to be consistent, right? So if you define Fourier transform in a certain way, that immediately fixes what the inverse Fourier transform must be. Okay, so let's see what happens if f of, so the statement is the following: if f of x is even, then so is g of alpha, and if f of x is odd, then so is g of alpha. This doesn't care about what factors you ascribe to them, right? Clearly. So let's see how this this follows directly from the definition. So if you want to pause the video and work this out for yourself, please feel free to do so. So the argument is straightforward. So we write down we have the expression for g of alpha, so we are able to immediately write down an expression for g of minus alpha. So you just replace alpha by minus alpha, and then you have 1 over 2 pi integral minus infinity to plus infinity f of x e to the I alpha x dx, right? So now if you change the variable of x to minus x, right? So I mean, you can use some other dummy variable, it doesn't matter, but it's convenient to just rewrite it in terms of x in the end. So then you have x becomes minus x, so again this e to the I alpha x will become e to the minus I alpha x, dx will become minus dx, and your limits also get changed. So this factor of minus 1 which comes from dx, and this reversal of the limits, if you if you do both of them, then you might as well do nothing, right? So you can just write down g of minus alpha as this expression 1 over 2 pi integral minus infinity to plus infinity f of minus x e to the minus I alpha x dx. From this expression we immediately conclude that if f of x is odd, so is g of alpha, and if f of x is even, then so is g of alpha, right? So if f of x is even, then f of minus x is going to be equal to f of x. So then of course you immediately see that g of minus alpha is going to be g of alpha. On the other hand, if f of x gave you a minus sign, that will reflect in g of minus alpha as well. So g of minus alpha will then become minus g of alpha, and therefore you see that the oddness or the evenness of a function gets reflected in the oddness or evenness respectively of its Fourier transform, right? So because of this, we can define, what is called a Fourier sine transform if you have an odd function, right? So if you have an odd function, so if we have seen that, all the information for, pertaining to your function is contained, in the interval 0 to infinity itself. You don't have to go from minus infinity to infinity, right? It's whatever information is available, to the right of the origin, it has full information about for all values of x to the left of the origin as well, right? So the definition for right, so here we have used a symmetric way of splitting these factors, right? So this is just some convention. Again, like I said right at the beginning, you have the freedom to pick these coefficients. So I am just using a symmetric, a definition in which these coefficients are shared in the same in an identical manner between the forward transform and the inverse transform. So if you have an odd function, right, so you just have to look at this and convince yourself that this makes perfect sense, right? You can start with your original Fourier transform as it is, right, and then you see that the integral from minus infinity to plus infinity can be written as just the integral from 0 to infinity with appropriate factors, right? So so now you have, so the definition for this, the Fourier sine transform is simply given by square root of 2 by pi integral 0 to infinity fs of x sine of alpha x dx, and the inverse Fourier transform gives you a representation for your function in terms of this integral, right? So integral from 0 to infinity gs of alpha sine of alpha x d alpha, right? So this is to be viewed in parallel to these expressions, and so you see that instead of your limits going from minus infinity to plus infinity, here it will go from 0 to infinity. And similarly, there is the notion of a Fourier cosine transform. Once again, even in an even function, all the information about the function is contained in the right half of your x-axis. You don't have to go to minus x at all, right? So here it makes more sense to work with cosines, right? So you have, the sine part is going to cancel, right? So it's only the cosine part which will live, and so you have 0 to infinity g, so f of fc of x, right? The subscript is, tells you that it's a Fourier cosine transform is in play, and it's an even function. So you have square root of 2 by pi integral from 0 to infinity gc of alpha cosine of alpha x d alpha, and the Fourier cosine transform itself is defined as gc of alpha is equal to square root of 2 by pi integral from 0 to infinity fc of x cosine of alpha x dx. So Fourier transforms have lots of applications. So let's just look at one example, and here we will actually use work with a function which is even. So consider this non-periodic function f of x is equal to 1 from minus 1 to 1, and it is 0 if mod x is greater than 1, right? So this can certainly be expressed as the Fourier transform of this function can be taken, although you cannot expand it as a Fourier series unless you extend this function, right? So we have seen that in the past. So we have seen how, if you're just given a function in some interval, you can assume that it's, for certain applications, it's useful to think of this as a periodic function whose one period information has been given, right? So but suppose we don't do that, right? We can do a Fourier transform of this function, and since the function is even, it is convenient to find its Fourier cosine transform. So now we have gc of alpha is equal to square root of 2 by pi, right, like we have seen the definition. So the integral is from 0 to 1 cosine of alpha x dx, and then you have, so that gives you a sine of alpha x divided by alpha, and the limits are from 0 to 1, and so only the limit at x equal to 1 survives, and so you are left with square root of 2 by pi sine of alpha divided by alpha, right? So if we invoke the inverse Fourier cosine transform, right, if gc of alpha is the Fourier cosine transform of f of x, then f of x must be the inverse Fourier cosine transform of GC of alpha. So which means f of x should be written as this Fourier integral 2 by pi integral 0 to infinity sine of alpha divided by alpha times cosine of alpha x d alpha. And so this result immediately yields us a very useful integral which appears in many contexts, and so that is obtained by putting x equal to 0. So we see that you can plot this function and see that at x equal to 0 there is no there is nothing weird about this function at x equal to 0. It's super smooth, it's well behaved. X equal to 0 is continuous, all the nice properties that you can want for your function are satisfied, and so the left, surely this integral is going to converge. So and it's going to has the value 1. So if we put f of 0 equal to 1 equal to 2 by pi integral 0 to infinity sine alpha by alpha d alpha, right? And then we bring this factor of pi by 2 to the left hand side, or you rewrite the whole thing. So basically what we have managed to show is this integral 0 to infinity sine alpha by alpha d alpha is equal to pi by 2. So this is a very useful result. This can be proved in other ways, right? But we see how the power of Fourier transform, right? So this example is an exercise in illustrating how Fourier transforms also can do magic tricks for us. So we saw how Fourier series can sometimes get us infinite series, and there are these magic results which we have shown some examples of, and there will be homeworks along this as well. But so the point is that Fourier transforms can also give us these kinds of magic results, and just one simple example of which has been illustrated in this lecture. That's all for this lecture. Thank you.